Hello, everyone. Welcome back to the AAS YouTube channel. This is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Christina Hedges with us today. Hey, Christina.
Hi.
How are you?
Yeah, doing really good.
Good. Where are you located at, Christina?
I'm based in California in the Bay Area.
Oh, okay. Very nice. Let's see. It is October 20th, 2021, as we're shooting this. And usually California kind of gets its best weather, I think, anyway, in October. So how is the weather there for you relative to what you're used to?
Yeah, it's cooling off a little bit, which is nice. Some of the leaves are a nice color now. It's a little chillier, which is nice. So
The morning chill
yeah.
arrives. Very good. And then it heats up.
Mhm.
Same thing. I'm in Phoenix, and it's a little chillier in the morning, although most people would think it's fairly hot in the morning if you were not living in the desert. And then we'll heat up to we'll get up to mid 80s today, upper 80s today. So we're still warm, but we've definitely turned the corner post equinox. So it's very nice. So it's very good. What is your position there? Where are you working at, and what you doing?
So I work at NASA Ames, which is here in Silicon Valley, and I'm currently a researcher. I have some NASA grants, and I found myself as a research scientist.
Very cool.
Previous to this, I was a support scientist for the Kepler Mission.
Okay, nice. Very good. Yep. Bay Area. Yep. Used to live there for a little while.
Yeah, it's nice.
Like it a bunch. Very cool. So Christina, what do you like to do for research?
Ooh, what do I like to do for research?
Yes.
All sorts. So mostly I focus my research on astrophysics with space-based telescopes, mostly focused on exoplanets, stellar variability, some young star stuff. And mostly I use Kepler, TESS, and HST to do my research.
Okay.
I also care about solar system objects.
Okay, nice. And that is going to bring us to a related topic on that research, a very pragmatic aspect. And bring this up. This is an AJ article in Linearized Field Deblending Point Spread Function Photometry for Impatient Astronomers. Love that title.
Thank you.
And Christina, take us away.
Yeah, so this is exactly what it says on the tin. This is a sort of new method for doing point spread function photometry, or Psf photometry, if you're a very impatient astronomer like me. The sort of few camps that there are of different kinds of photometry that you can do for missions like Kepler and TESS, it tends to be aperture photometry, and you can change how you build an aperture. There are some other kinds like difference imaging, which are very interesting. And then Psf photometry. Psf photometry is where you have a model of what you think your telescope is going to look at. And then you use that model and try and fit it to any image that comes from the telescope. And then you fit to find the flux. Simple aperture photometry, though, you just like pick pixels and then you add them up, and that's really, really fast. And so the difference between these two methods really is that aperture photometry, it's fast. Psf photometry, it's slow. Psf photometry tends to be a bit more accurate, particularly if your images aren't well registered, because you can move your Psf model around in the image. Aperture photometry, you can't account for things like crowding and contamination. So that's a big downside, but it's fast.
Right.
And so the idea here is that we're showing a different kind of method, which is a sort of hybrid of the two approaches. And this method will let us get access to that precise information and will let us deal with crowding without having to undergo like the detailed fitting of PSFs on an individual star basis.
Best of both worlds. Very cool.
Yeah, so I think if we go to, can we go to figure 1?
Sure. There's an intro or photography and figure 1. There we go. Kepler PRF.
Great. So the Kepler mission is the mission that we decided that we were gonna use this new method on. We've chosen Kepler in particular because Kepler is really stable. It has lots and lots of data, and because this is something that we're very familiar with. So myself and 2 of my co-authors, Garrett and Jesse, both worked for the Kepler mission, and so this is something that's really within our wheelhouse. We know a lot about the telescope. Then another of my co-authors, Rodrigo Lugo, has also worked a lot with Kepler and K2.
Mm-hmm.
Then recently, Jorge Martinez Palomera has joined our team as a postdoc working on this data and other data sets. And so this was something where Kepler is really within the wheelhouse of all of us. On the screen now, you can see the PRF of Kepler for a particular channel of the detector.
Mm-hmm.
So PRF and PSF are slightly different things. And in this paper, we have defined them in this way. PSF is the optical point spread function. It's what happens to the light when you come through all of the different optical paths of the detector, or sorry, of the telescope. The PRF, which is sometimes called an EPSF or effective PSF, is what happens when you measure that on the detector. So it's the pixel response function.
Mm-hmm.
This is Kepler terminology, and so we have measured this PRF. Steve Bryson has measured this PRF for the detector, and so this is like common nomenclature within the mission, this PRF.
Okay.
And so this is what we're fitting. We basically can't have access to just the PSF because we only ever get it convolved with the detector.
Mm-hmm.
So this is really what we're fitting. The one that you can see on the screen is for a particular channel. You can see that it's kind of elongated in one axis. There's this kind of lump off to one side. This is in log space, so it's very, very bright in the middle, and then it has these wings which extend pretty far out.
Yep.
Yeah, and so this is something that we would like to fit. Now, the trouble with fitting this sort of shape, oh, please go ahead.
No, go ahead.
Oh, sorry. The trouble with fitting this sort of shape is that, especially if you want to fit it a lot, you need a model that's very, very fast to evaluate. You need to be able to come up with a model that fits this shape really well and it's super fast to evaluate. To do that, you have to capture all of the detail in the model, and that includes the fact that it's very peaky in the middle, and it's got these broad wings, which are very important to the shape. If you're in a crowded region, you're actually going to use these wings to try and disentangle two sources.
Mm-hmm. Yep.
So very important.
Yep.
So part of this paper is discussing good ways to come up with a simple model for this PRF shape. And there's two ways to think about this problem, which we've introduced, which are kind of new ways to think about it, which is simplifying assumptions, which make fitting a simple model to this much easier.
Okay.
The first one is you should fit in this log space. It's much easier to make a beautiful, linear, simple model if you're going to fit in this log space.
Okay.
So fitting this PSF model, we're going to build a shape model, which is just for the PRF shape across many, many targets, and we're going to do that in log space. The second simplifying assumption is to recognize that this shape has a lot of symmetry in a radial dimension.
Yeah.
It's radially, it's azimuthally quite symmetric. It has some round shape to it. And so it's much better to fit this in polar coordinates than it would be in Cartesian coordinates.
Okay, sure.
And so what we can do is we can take all of the data from a particular portion of Kepler. We can take all of the sources and identify them using Gaia. We can extract their flux, have it in log space, and fit a polar coordinate model to this shape.
Okay.
In order to make it a simple, fast, linear model, we're going to fit with something called basis splines, which are just piecewise polynomials.
Yes.
And so the fast, simple model that we've come up with to fit this shape is to say polar coordinates, log space, basis splines, simple, linear, piecewise polynomial.
I'm with you.
Right. You can go to the next figure, I think figure 2.
Okay. Trending, simplifying, you talked about those, and there we go, figure 2. Let's blow that up. There we go.
Excellent. Okay, so this figure is showing what I previously said, and it's put it into practice. So on the top left-hand side, we have the data. This is data we've extracted from about 400 sources in a small subset of Kepler data. We've extracted all these sources using Gaia.
Okay.
In this work, we have made the assumption that Gaia, as far as Kepler is concerned, is the truth.
Okay.
Kepler has pixels that are quite broad compared with the resolution of Gaia.
Mm-hmm.
And so as far as Kepler is concerned, Gaia might as well just be the fundamental truth of the universe.
Okay.
So we extract this data, which is taken from these Kepler targets. We've done some cleaning here to remove targets that are very contaminated. We don't want those to contribute to our model. And we've done some clipping to get it down to this, to sort of remove the faint pixels around the edge. So we have this kind of tooth shape.
Okay. Yep.
So that data is in terms of delta X, delta Y in arc seconds. So this is distance from the center of the source as given by Gaia. And then this is the flux that Kepler records. Again, we're in log space. So yellow, very bright, blue, very faint.
Yep. Okay.
Top right-hand side now, we have our model for this shape. This is our model in polar coordinates built with a basis spline, which is piecewise polynomials. In this work, we we developed an algorithm for making a polynomial basis spline which wraps in this angle phi.
Okay.
So here we want, this is given in minus pi over 2 to pi over 2, I believe. Or no, I'm sorry, it's minus pi to pi. You want minus pi to wrap and influence pi. We know that there should be no discontinuity, there should be no edge.
Right.
And so coming up with a spline that wraps in that dimension is something that we've added into the appendix of this work.
Cool.
So you can see that model is really nice and smooth. It will not have a nasty break at that pi minus pi point, and it is smoothly varying in radius. There are a small number of components to this model. I want to say ballpark tens of components to this model to fit all of these pixels. Okay. You can see on the, so the bottom row is our model and the top row is our data. So you can see our data in this Cartesian or polar coordinate and Cartesian coordinate on the left. And on the bottom, you can see model in polar coordinate and in Cartesian coordinate. Okay. The thing that you can see is that the model matches the data really nicely. It matches the data really nicely in the wings and in the center, which is exactly the thing that we needed. Cool. And this model is fast, simple, linear. Cool. So this is our easy way to make a simple PRF model given the data that's flexible, captures all the information. I think we can go to the next figure, figure 3.
Yep, here's the wrapper.
Oh, we could talk a little about those equations. Maybe let's start with figure 3 first, and then we'll.
Yeah, go back to the equations. Perfectly fine.
All right. Great. Okay. So to get to this figure, there's some equations that maybe we can go back to and chat about. I want to focus on the gray line in this figure. Okay. So what we've done in our previous figure is we've generated this model, and it fits really nicely to all the different parts of the Psf that we measure. What we can then do is we then instantiate that model at every point that Gaia says there's a source. And as is discussed in some of the paper portions before this, and maybe I'll go into more detail here, what we can do is we can build a giant, very sparse matrix where we have each vector in the matrix has that Psf shape model that we built, and it's valued close to where the source is. And then we can have a matrix which is filled with thousands of those vectors, one per every single source, and they're fixed in position.
I'm with you.
What we're then going to do, we have that giant matrix, is we're going to fit that to every cadence of data that we have. Every time, every image that the telescope took a picture of, we're going to fit that matrix. And essentially, we've got a scene model. We've got something which says, Gaia knows this is where the sources are. This is the shape that the sources should be, given what we know about Kepler. Now all we have to find is the amplitude. We've fixed position. Okay. And that then gives us our flux. And so on the screen now, you can see this gray light curve. That is for a particular source. And I've picked this one because it's got some nice variability in it.
Indeed.
For this source, we fit that giant matrix one per time, and we get that weight value, that amplitude value. Yeah. When you plot that as a function of time, you can see the variability of the source. That's great. The gray is what happens if you just do exactly what I've said. And you can see that it's like wonky. It's got this like tilt in it. Yeah. And that doesn't look good. That doesn't look right. And so what's happening here is Kepler and TESS and all sorts of instruments out in space whizzing around the Earth have something called velocity aberration, which is a relativistic effect where sources appear to move and all as one. Sources appear to move in the image over time as the telescope moves. This is unfortunate because this breaks our assumption that Gaia knew exactly where everything was, because now everything's going to move. And that's really crummy. We don't want that, because that's introducing this drift where over on the left-hand side, it's as though the source is quite far away from that fixed position that Gaia told us, and so we're recording lower flux. But luckily, we have come up with a good fix for this.
Okay.
Would you be able to go back to the equations that were, I think, above this page, and that it shows some matrix operations?
Indeed. So we're going to set up, there's our design matrix, there's our vector, and then we get into some of the matrix operations. So what would you like?
Let's see. Okay, so the equations that we see on the screen now, I just have to get myself familiar with exactly where we are in the paper.
Oh, I understand this thing. This phenomena.
Yeah, okay, great. So there are lots of different matrices in this work. The idea here is that we have design matrices, which are this piecewise polynomial that you can read a little bit more about in the appendix. We have one in R, which is this radial direction, and one in phi, which is this angle dimension. We then create a 2D design matrix by just taking the multiplication of these two different matrices to make one two-dimensional matrix. It has dependence both in the radial dimension and in the phi dimension. And then all we do is we fit this to the data that we have. We're fitting it in that log space. Then we get on to 4.4. Once we have that data set, so we've solved x dot w, we've solved to find that w, which is the weights of the shape model. So this is fixed our shape model. Then in 4.4, we're going to take this shape model and we're now going to fit it to every single source. So our shape model is now 10 to the power of this design matrix that we've built, dotted with some weights that we've estimated, which is that equation 14.
Yes.
What we're then going to do is we're going to create lots of S's, which is this shape model, one for every single source, located at all of the sources that Gaia thinks.
I'm with you. That gives
and
you
then,
this.
Yeah, and then all we do in equation 16 is we're fitting to find V, which is now this second set of weights, and this is the flux of every source. So we get V, which has dimensions, number of sources, and then we just fit this for a number of times, and then we get this giant set of flux as a function of time for every source.
Got it.
Okay.
I'm with you. Okay, I'm with you.
Excellent. So now we're going to talk about how we do that velocity aberration correction. So yes. I think, can we go further? Yeah.
Where we would like. Want to go down.
Let's go to the next set of equations. Let's go here, motion.
Yeah. Sounds like it's got some aberration component to it.
Absolutely. Okay, so this is what we're now going to do in order to fit our velocity aberration. The thing that we want to do here is not fit every single source individually so that we find the location and the amplitude. That's Psf photometry, and that's expensive. And you tend to find that it's very degenerate, especially when you have sources that are drifting off the edge of the detector, fitting for amplitude and position. They're degenerate. I could move it further off the detector and that would change the flux.
Yes.
So what we want to do is we want to take the scene model that we've built and we want to move the whole thing. We don't want to change the relative positions of the sources. We just want to move the model around.
Okay.
And we can do this kind of fairly easily. What we're going to do is we're going to take the flux that we've measured from the Kepler detector, and we're going to extract all the pixel time series for sources that, again, aren't contaminated.
Okay.
We're going to extract those time series and we're going to mean normalize them.
Okay.
And we're going to use that. Yeah, exactly. And we're then going to bin this in time. We don't need all of the time resolution here to fit this model. So we're just going to bin it, which means that we're using less data and it's easier to invert a giant matrix that's coming up. So we're going to bin this down, and we've binned it, I think, to something like tens of points in time, about 20 points in time. That's down from, for Kepler quarter, it's about 4,000 points in time. So great reduction in time resolution here.
Yep.
I think I'm going to put a pin in equation 18. Can we go to the next figure? Because I think it's easier to see in visually what's going on before we dig in. This is the one.
Figure 4.
This is the one. Okay, so what we're looking at now, we've got data again on the top row and model on the bottom row. I want us to focus on the data. The data here is that thing that I'd said, which was take all of the pixel time series and mean normalize them, and just look at them as a function of that delta x, delta y. This again is in arc seconds.
Mm-hmm.
The thing that you're seeing now in this color space is flux relative to that mean. So
yes,
blue here is it's about half as bright as the mean, and red here is it's about 50% brighter.
Mm-hmm.
What you can see on the top row is the left is the first cadence and the right is the last cadence. You can see that they're trading off. You can see that they're moving. Blue goes to red and red goes to blue. And that's because of this velocity aberration. All of the sources are moving in the same direction.
Yes. Okay.
Mm-hmm. All we have to do to account for this is we have to come up with a model which describes this delta. I'm calling this a delta flux. It's a change that we could apply if we could multiply any shape model by this delta. It would move that shape model around.
Yep.
All we need to do is find a model that accurately describes this change from the mean, this delta from the mean, and then we multiply our shape model by it, and that will account for this velocity aberration.
Okay.
So the model that we've built is on the bottom, very similar principles as the model before, except in this case, there's not really any radial or azimuthal symmetry here. We're not capitalizing on anything that's round. It actually shouldn't be round. It should be very Cartesian. It should be the whole image moving. So fitting in Cartesian space,
Yep.
It's valid. So similar thing, basis splines fitting this polynomial model. Now with, instead of it being a function of space, it's now a function of time.
Yes.
So you can see on the bottom, this is a model that we fit, and it fits pretty well. It fits pretty well to get rid of this velocity aberration.
Uh-huh.
I think if we go back to equation 18, it'll now be easier to explain what's going on.
Okay.
And then if we look at equation 19.
Mm-hmm. So we got our B.
Yeah.
Here's our delta.
Okay, so these are now 19 and 20 are the Cartesian design matrices that we're using to build this time correction model. We're looking at just the Cartesian space, and we're going to build up basis splines in delta x, delta y.
Okay.
What we're then going to do is we're going to turn this into column vectors. So we're going to take the first column of x dotted with the first column of y. We're going to take the second column of x dotted with the first column of y, the third column of x dotted with the first column of y. And we're going to keep going until we've gone through all of the columns and we have just one giant column matrix, which now has 2D, two-dimensional dependence.
Uh-huh. Okay.
This has given us one matrix. And then now we're going to add in a third dependence, which is time. And so equation 23, you can see we've taken that giant column matrix and we've now we have now multiplied it by this time polynomial, which is time to the power of 0, times to the power of 1, times to the power of 2, times to the power of 3.
Mm-hmm. Okay.
We've had to do some binning here, which is where equation 18 and 17 comes from, because now A is enormous. A has shape. You can actually read it here. A has shape, and it's got to be sources, pixels, number of time bins,
Yes.
Resolution that you had in space, resolution that you had in time. It's a huge matrix, and you're going to have to invert this in order to find the best fitting weights for this model. And so to do that, we've had to bin. Like, we couldn't have all of the time points in. It makes the matrix completely untractable to invert. We also don't really need that level of detail because it's a slow drift. There's not a lot of detail in velocity aberration. It's just a slow drift over time.
Yep.
So
Okay.
what we do then is we fit to find these weights. Then once you fit them, because it's a simple polynomial, equation 24 basically says that this change, this delta that we're going to apply at any given time I, at any ith time, is simply the weights you fitted, which is u hat, dotted with that A matrix multiplied by the time index I. So you've gotten away from having to use every single time. What this means is for every single ith frame, there's going to be a shape model, and there's going to be this delta correction Li, which is going to move it, and it's going to move that shape model so it's in the correct position for the correct velocity aberration.
I'm with you. Yep.
Right. So if we go up to figure 3.
Okay. Let's go back to figure 3, and now we'll understand this figure better.
Now we can see that the black line has velocity aberration corrected. And you can see that it's now gotten rid of a lot of that egregious slope downwards.
Right.
Now it's much more flat. And this is because the whole model is moving in accordance with the velocity aberration of the scene.
Okay.
Yeah.
Cool. Good.
Cool.
Good.
So I think, wait, do you have any questions?
No, I am good right now.
Excellent. So I think we can go to the next section, which is very fun.
Okay. I like fun.
I think it's fun. You'll be able to see why I think it's fun. So there's a little flowchart here which helps go through the steps in the model, and I can talk about that just briefly. You start with a stack of images, which, you know, Kepler, TESS, it doesn't matter. Start with a stack of images. We estimate a rough circular aperture and guess an initial shape model. We build our shape model, and then we iterate so that we're getting rid of significant crowding, and so that we're getting rid of any pixels that don't really contribute. And this lets us hone in on the correct shape model. Okay. And then if we're not going to do any velocity aberration correction, we just fit that to every single source in the scene. And if we are going to do the velocity aberration correction, we add that L matrix that we were just talking about. We add that delta correction in.
Right.
Yeah.
Good.
So we can go, I think we can skip figure 6. This is talking about how close we are with PDC-SAP flux, which is this corrected pipeline flux from the Kepler mission. Yeah. Oh no, here we go. Yes, figure 6. I'm sorry, this is perfect. This is exactly where we want to be.
Okay.
So this is what I think is fun. You can tell that I think this is fun because I used to work for the Kepler mission, and like during the K2 phase, I think this is wicked. Cool. So on the right-hand side of figure 6, you can see this little postage stamp. It's got little pixels in it. That's the one. This is a Kepler target, and this is actually a KOI, a Kepler object of interest, and it's KOI 608. Okay. KOIs are objects where Kepler identified a transiting signal that was consistent with being a planetary size, but for a reason of a host of reasons, it was discounted as a false positive. Okay. KOI 608 was discounted because there was a significant centroid shift, a change in where the center of the flux was during transit, indicating that it probably had a background something going on, and that it might have been a background eclipsing binary that was the true source of the transit, and so it got thrown away. Okay. With this method, as I sort of said way back in the beginning, the idea is that it's fast, but it lets you deal with crowding. It lets you deal with contamination. Gaia is well capable of identifying that there's actually 2 sources in this image. And this is information that Kepler didn't have. Kepler thought, you know, at the time, this was considered to be one source. Right. So here we are, Gaia data, and we can tell that there are 2 sources. There's the blue one, which is the source that Kepler targeted. And there's the orange one, which is much fainter and in the background. Okay. They're about, I think they are it's 2 magnitudes fainter. So orange is 2 magnitudes fainter, and it's separated by just about 1 pixel. Wow. Okay. Yeah, so pretty well blended, and orange is pretty faint. So on the left-hand side of figure 6, the blue light curve at the top and the orange light curve at the bottom are the 2 sources that we've extracted using this new method, using LFD photometry. Okay. In the lighter colors in the background, that's without a velocity aberration correction, and then the colors in the foreground, the darker, more solid colors, those are with our velocity aberration correction. Significant flattening out there. Okay. Yeah, absolutely, significantly flattened out, and it's much better, especially when targets are very, very close together. You do want to account for that velocity aberration because otherwise it's going to be much harder to disentangle them. So now what we can do, we've pulled these 2 light curves apart. Now we can look at where was the transiting signal coming from. Kepler identified the signal, which source is it coming from? And so that's figure 7. Figure 7, you can see in black, the light curve that came out of the original Kepler mission. You can see there is this little transit in it, and this was flagged as something that was maybe consistent with an Earth-sized planet, but centroid shift, it's a background eclipsing binary, get rid of it. Okay. Blue and orange are the light curves that we've extracted using LFD photometry. And you can see that there is no transiting signal around blue, the main mission target. And there's a much deeper transit around orange, this background target. And despite the fact that it's 2 magnitudes fainter and separated by just a pixel, we've really well separated these two signals. And we can now tell that the transiting signal is actually about 2-ish Jupiter radii around the orange star, around this background star. I think it was 2-ish Jupiter radii. Maybe it was a bit more.
Yeah, 2.5.
Yes.
Yeah, table 1.
So this is like potentially substellar sized object or small star object going around the background source. This demonstrates that this method is really well able to separate even extremely well crowded Kepler targets. Even I've actually used it and found that even sub-pixel, we can still separate them. And even in cases where the magnitudes are very, very similar, so you've got sub-pixel, same magnitude, looks like an identical source, and you can still separate them using this method.
That is awesome.
Yeah, so I think
maybe you'll hit this later, but I'll ask now. So this is an example of taking a false positive and showing it's actually a positive. Does one have do you yet have a sense of how many false positives might actually be real positives?
So let me give you
90%.
So I think that the Kepler mission asked a question, which was, if I target these very carefully selected stars, how many planets are around them? And so to the Kepler mission, even if this were an Earth-sized planet in the habitable zone, it wouldn't necessarily be a false positive in that it doesn't ask, it's around a background star. And so this wasn't something that was targeted by the mission. So it's okay to say that this isn't really part of a sort of Kepler sample anyway. This isn't a false positive. However, there are a lot of KOIs, I think about thousands of KOIs, some of which have been discounted again because they have this centroid offset. And so I don't have the answer for you right now. How many of these can we separate and ask the question, what are these transiting signals? But we are certainly going to answer this question.
Cool. Didn't mean to put you on the spot there.
No, this is great.
Okay, very nice. There's a real world example of this. Very cool.
Yeah. So I think the next section is probably the appendix. I don't think we have any. Yeah, this is a figure that compares our precision with the pipeline precision. We do comparably, which is excellent. We produce comparably precise light curves in the set that we tested. And I think that should be the last figure other than the appendix.
Okay, and I wanted to
great.
Oh, you're using B-splines. Okay, I'm good.
Yeah, absolutely. So the appendix just goes through how we're doing the linear fitting, how we're doing the how we're building basis splines. It's just basic information to sort of support the main work. There's also a long table of all of the parameters we used and what they all mean.
Oh, this is great. This is really good because sometimes when you read a paper when it has this much symbology to it, it can be painful to try and go through the article. And now, where is F bar defined? Oh, here it is on page 3, buried in the second column. Or here it makes it very clear, what the symbols mean. So I really appreciate. And with this much symbology, defining in a single table what is going on. So no, I really like this.
This is actually this is something that Rodrigo, who's a co-author, second author Rodrigo, has taught me, and I'm well into his school of thought on this.
Good. Very cool. So let me ask one final question. Is I imagine you're a proponent of open source, so is this available for people to try out on other stuff?
It sure is. So yeah, absolutely. So moving forward, this is the first paper and hopefully a series of papers. This one describes the method and demonstrates that it's powerful. The tool that we built to do this is available online on GitHub in our group repository. You can absolutely get it, download it, try it, break it. It's called Psf Machine.
Okay.
So you'll be
There we go.
There it is. There it is.
Machine, GitHub, SSD, Data Lab, Psf machine.
That's it.
Get out, people. Go get it.
Oh, and I guess I forgot to say that like this is very tractable on like a small computer. I did this on my like
Yeah.
2017 MacBook, and you know it does things in I think tens of minutes. It'll do like one fit in 5 minutes for 500 sources and extract all of the photometry for 500 sources.
Pretty good. Otherwise, it's that machine would be grossly underpowered if you had done it the traditional.
Yes.
Traditional
Yes. I think so. To get that amount of photometry out with this kind of precision.
Very nice.
So yeah, we absolutely do have it on GitHub. Please go check it out and break it. The current way forward. So Jorge Martinez Palomero, who's a co-author on this work, is working with us to apply this tool set to the Kepler data now. So Jorge is in the process of extracting lots of photometry from Kepler and getting access to all of these background and blended sources. And he's currently in the process of improving some of the things that we did in this initial paper, mostly improving the velocity aberration correction. It's possible to actually do a little bit better than we said in this, flattening it out more. Cool. And so we're really hopeful that we'll be able to extract more interesting variable stars from Kepler.
Cool. Christina, I want to thank you so much again for walking us through this very lovely opening paper. Very nice. And you touched on it a little bit there at the end. You know, is where does this work go? And so, you know, one aspect was, you know, making the velocity aberrations even flatter, going through additional Kepler fields and so on. So let me ask, you know, where do we go, let's say, over the next 5 years? And you don't have to spill your next research projects or something like that. But, you know, where does this work go after the immediate things that you just mentioned?
Yeah, absolutely. So in the very immediate term, we're working on applying this, like I said, to Kepler and getting access to those background sources. In the medium term, Jorge is going to be updating this to apply to K2. Now K2 is Kepler, but it had a lot of motion in it. It was focused in the ecliptic, and K2 had this roll motion. Right. And so it's going to be harder to extract photometry with this method, but it just requires a slightly different time correction. And so once Jorge's finished extracting all of the background sources from Kepler, we're also then going to be looking at how do we get the background sources from K2. We're going to be looking at a lot of the cluster data and trying to get really good, precise light curves out of this crowded regions. Okay, very cool. And of course, Plato is a mission coming up. Yeah. Plato's coming up. We've got tests. So the methods that I talked about in this paper, they're very applicable to any similar mission, and tests Plato, they're very similar. Anything where you've got lots and lots of stars so that you can estimate your Psf, it's going to be a method that you can absolutely use. And we've tried to engineer the tool so that it's fairly agnostic of what you're trying to do. Right. If there are particular instruments that people want to use that don't go well through Psf machine out of the box, please just leave us a comment on the GitHub and we'd love to chat to people about it. Awesome. Very cool. Very cool. Christina, thank you once again. Appreciate it. And that'll do. And I hope this made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye-bye.